So welcome everybody to our regular seminar. Today's visitor, Joshua Soderholm, from the School of Geography, Planning and Environmental Management, is that correct?
Yeah.
Yeah, at the University of Queensland in St. Lucia, and Queensland is Brisbane, right?
Yeah,
Effectively.
that's right. Yeah.
Suburb of Brisbane. Joshua finished his PhD last year at the University of Queensland, got his bachelor in 2010 in mathematics and geographical science, and PhD in meteorology. He's going to start after this visit here at NCAR, postdoc position at the University of Queensland. His dissertation explored the climatological and meteorological aspects of sea breeze interactions with warm season thunderstorms in South East Queensland. And as part of his PhD project, he established the UQ-X-Pol mobile radar, and maybe you'll tell us a little bit
more about that.
Okay, great, thank you. Which he established, and it has seen several successful deployments across Australia for both convective and brush fires research. In addition, Joshua has also worked on radar applications for the energy distribution and insurance sectors, and is a keen collaborator across operational, industry, and amateur meteorology groups. I was quite surprised. He has 9 publications, including 3 first-authored papers already, which is quite a lot. Just have finished a PhD, so I've been pretty busy, which is good. And I'm really curious to hear your talk for today. The topic, outcomes of the Coastal Convective Interactions Experiment, CCIE, and new horizons with the Australian Radar Network.
Thanks,
Please,
Mike.
Joshua.
Cheers. Thanks, everyone, for coming along on the Eclipse Week. So I'm giving two very different topics today.
Sorry, can you just turn your microphone on?
Oh, was it on? All right, let's just switch. Yep, all good. Thanks everyone for coming along. So I'm talking about 2 very different topics today. The first one relates to my PhD, which concluded last year. It was titled the Coastal Convective Interactions Experiment. And the second topic I'm talking about is current and upcoming work across the Australian Radar Network with the Bureau of Meteorology. So just some of the topics under those which I'll be talking about. I'll be talking about my PhD project, the climatological findings and the field experiment findings. And in regards to the Australian Radar Network, I'll give you an overview of what we got. Have a look at our plans to develop a national archive of radar data that's freely accessible. Looking at how this data can be used for climatology applications in industry and also nowcasting. There's a lot of appetite for that out there. And also looking towards the future, in particular dual pole. All right, so next 15 minutes, I'll give you a summary of my major findings from my PhD project. So this is the region which I studied in Australia, down here on the east coast. We call it South East Queensland. In the centre of South East Queensland is the capital city of Brisbane. I'll go over all these details later when I talk about the field experiment, but I just want you to observe at the moment we have this, the Pacific Ocean, in particular the Coral Sea, on the right-hand side. We have a lot of elevated topography, what we call elevated in Australia, 1,000 metres. In sort of almost an arc around the region, and a lot of agriculture and dams. So quite a complex physical landscape. And this is all across scales of 100 kilometres west and 150 kilometres north-south. So quite small, compact. This region is very well known for its thunderstorm activity, in particular hailstorms. When I started my PhD, I had a couple research questions. On the right over there, I wanted to understand the climatology of thunderstorms in the region, what were the meteorological and the climate drivers. I want to understand how these drivers are actually physically influencing the environment, how are they changing the meteorology. And finally, the big question which we keep asking ourselves in Brisbane is we get these seemingly marginal environments in the morning, and the prediction is for thundery showers. But by afternoon, we'll have orange-sized hail falling on the capital city of Brisbane. And picking out these high-end days from our broad spectrum of marginal days is a big problem for us in South East Queensland. So starting off with the climatology research. So quickly, just to brush for those who aren't familiar with how a climatology database is built of thunderstorms. This is derived from radar. So we start with our radar products, which we clean up, and then we grid onto a regular Cartesian grid. Then we look at running detection algorithms to pull out our thunderstorms. We track our thunderstorms in time and space. And then we analyze our thunderstorms. We try to estimate how much hail is in them. We have a look at their size. We have a look at the maximum rain rates and other measures. And then we put all this information together into a database to permit climatological analysis. For my project, I had at that time 18 years of radar data, so a reasonable record from a single radar in South East Queensland that hadn't changed in that time.
These are all non-polarimetric radars.
Yeah, at this time of my PhD, we had no polarimetric radars operational for the Bureau in Australia. So the hail measurements were single pole. So looking at some results, starting off with the spatial and synoptic analysis. So I took this database and I plotted up all of our hailstorms, which were derived by using the single pole mesh threshold. It's an estimate of hail size based on reflectivity, vertically integrated reflectivity. And using the threshold of 21 millimeters, I plotted the polygons of all the hailstorms across the entire record onto a single map and normalized it by the number of years to give us annual frequency. So this red line here represents the range, which encompasses South East Queensland. And you notice in parts of South East Queensland, we have on average about 0.7 hailstorms per year, producing hail 21 millimeters or larger derived from radar. Brisbane, marked here in this box, still experiences a considerable number of hailstorms, and in particular these hailstorms tend to originate from the southwest here. So you can see there's this hotspot activity with a lot of storms down here in the south, another band up here in the north, and less activity on the coast except around Brisbane itself, which is interesting. When we had a look at this database and broke it up by synoptic types, so we have 3 primary synoptic types in South East Queensland. These shortwave weak troughs which occur fairly regularly throughout the season. We have these stronger southeasterly changes which will often push through. They're not quite a cold front and they're more closer to what you'd call a trough, but they come from that southeasterly direction. And finally we have our continental dry lines which wax and wane across Queensland. When we plot up a statistical analysis of the number of hailstorm cells per hailstorm day, on average we can see that our southeasterly change, synoptic type, is producing a lot more. We have our higher mediums, higher tails, and our quartiles are slightly larger on the upper end as well. And in particular, I've divided southeasterly changes and our synoptic types up into sea breeze, SB, and non-sea breeze days. And there's a real peak on sea breeze days with this southeasterly change. So when we have a look at the total number of events, they're not all occurring on southeasterly change sea breeze environments. There's a broad spread across all the different environments. It's just the fact that on this combination of synoptic and mesoscale environment, we're having more hailstorms per hailstorm day, which made us think about how in particular the sea breeze is moderating thunderstorms in the region. Looking at the longer term temporal variability. So here on the left we have a time series plot from 1997 to, this is in financial years, to 2014. And on this plot, I've shown, first off, the number of days per year of hailstorms. So it's varying between about 15 and 40 days per year across the record for the entire South East Queensland region. And I plotted in the dashed bold line here the number of sea breeze days per year. On top of this as well, I've also plotted our proxy for ENSO, which is our Pacific Ocean climate signal, which dominates the southeast Queensland environment here. So SOI, the Southern Oscillation Index, it's a pressure differential index. And I plotted this here as a time series with the thin black lines. And you can see that there is a negative correlation between the thunderstorm activity, the peaks in the thunderstorm activity, and the troughs between the two records. And this shows up statistically as well when we adjust for the small sample size. So we're suspecting here that different phases of ENSO are moderating the thunderstorm activity across the region. We have a few hypotheses why that might be occurring, but it's a line of research we need to follow more up on. It's quite interesting to see, because people are always after seasonal predictions of thunderstorms. In terms of monthly frequency, much simpler story. We have our peak thunderstorm season in November, December every year. We have the maximum amount of hailstorm activity for that, hailstorm days for that month. So this is around 6.5 on average days per month for hailstorms in December. And our sea breeze activity peaks a little bit earlier as we get that transition from winter to summer in the cold oceans and the warming land in spring around September. So this sort of these plots really help us to understand what's going on in the background, in particular the long term with the climate variability. So moving on to the field experiment. So South East Queensland, as I mentioned, is really diverse in the landscapes we have. So we have, as I mentioned, our border ranges down south, and then our Great Dividing Range, a bit of our continental divide running north, south, across that region. We have lots of bays, we have our coral sea, so these are different sea surface temperatures across these two regions, and we get different sea breezes propagating off them. We have a large urban area of about 4 million people now spread across north-south, which modifies the local environment. We have large shallow lakes, which we've measured the skin temperatures around 32 degrees in the middle of summer. We have areas of remnant subtropical rainforest across our ranges, which are really good for convective initiation. We have a lot of dryland agriculture, we have a lot of irrigated agriculture, and of course on top of this we have our synoptic and climate regimes moderating thunderstorm activity across this really small but diverse region. So quickly looking at the instrumentation we used in the field, we had a 3-season field campaign with both fixed and mobile instrumentation. Starting off with, I know this map is a little bit compressed and I apologise for that, but we have a number of radars to start off with. We had Mount Stapleton, which is a single pole S-band Doppler radar, Marburg, an older WSR-74 S-band, and CP2 before it was decommissioned, ran for this project as its finale. On top of that, we have a radiosonde site at Brisbane Airport, and the black dots and the triangles represent weather stations across the region that we use to look at surface conditions. On top of this, we also ran our own mobile instrumentation. So this trailer here, I had a lot of fun setting that up during my PhD. We purchased a solid-state Furuno radar, dual pole, and we mounted that on this trailer along with a Grawl sounding system and a nice little Vaisala AWS as well. So we've had 3 really successful years in southeast Queensland with this, and also we've done a lot of bushfire work as well across the country with this setup. And this provided me more with the case studies. So we go out, we look at individual thunderstorm events of interest using this non-operational gear for field research. Looking at the near-surface meteorology from the field campaign, so we put together all of our additional surface stations and we computed these analyses for our fieldwork days. So this is a surface analysis for a particularly significant storm event on the 27th of November 2014. The colour shadings here represent theta E, so the redder are higher theta E in the near surface environment. The brown or oranges are lower theta E, so lower energy in the near surface environment. We've also contoured on dew points, so decreasing dew points away from the coast with the blue dashed lines. And also the red lines are our surface temperatures observed by the weather stations. So on this storm day, we see this pattern which we see over and over and over again in South East Queensland. We have high theta E over the city, high theta E over the irrigated areas, and a sort of an axis of lower theta E through the middle. Out here to the west, we have a lot of irrigation. We have corn, lucerne, lots of tomatoes, all these vegetables, and they're being irrigated twice a day in summer. Lots of black soil as well. So all our weather stations across this region pick up a really high dew point, driving this theta E anomaly near the surface. In the middle here we have pastoral land, dry land, and a large military base around this region as well. So we have earlier mixing in the morning and the lower dew points compared to the irrigated areas. And finally the city. The city is really interesting because it's driven not only by this urban heat island signature, but also by increased dew points. So starting with the urban heat island, we had a look at 4 city stations. So this is the Bureau's Brisbane station, the South Brisbane station, Woolloongabba and Central. These are all within the Brisbane city region, but this one is in almost a suburban area. It's actually not very densely built. This plot shows us the mean temperature difference between this station and the surrounding rural coastal stations. So the same distance from the coast, but in a rural environment. And you can see the medians for our stations in the very centre of the city are about 2.5, 3 degrees warmer on average across the field campaign. So we had a look at what was happening and comparing this to other research that's been done in this area. And we found quite a few papers which have linked urban heat island effects to enhanced sea breeze onset. And when we have a look at the data for the sea breeze onset across the Brisbane city region, we find that the sea breeze is occurring earlier in the day than the regions which are more rural, driven by the differential heating of the urban environment, which is a really nice find because it hasn't been shown this explicitly observationally before. So we have these three sort of different areas, but all driven by different local processes. Moving from the surface to what happens with the profile, for my PhD project, I'm mainly focused on the diurnal profile evolution. So what's happening on a day-to-day basis of heating, sea breezes, and processes like that. So looking at the top plot, this is our morning profiles, what it typically looks like. We have one conceptual profile here over the city environment, one profile here over our agricultural, irrigated agriculture further inland. What we typically have is we have weak northerly flow on most of our storm days. We have no low-level jets in the subtropics. So we have very ambient flow in the low levels. And then aloft, around the 2 kilometre mark, we usually have prevailing westerly flow at the top of the boundary layer shown across here. So in the morning, our boundary layers are developing, they're warming up, and they're deepening. They're quite similar between the agricultural areas and the city at this point in time. Later on in the day, by 3 p.m, our sea breeze starts to dominate the lower atmosphere in the maritime environment. So our sea breeze moves across Brisbane. While further inland, away from the sea breeze, our boundary layer has continued to deepen. And as it continues to deepen, it deepens into this prevailing westerly flow. And this westerly flow pushes our continental boundary layer on top of our coastal boundary layer. So you see you have, with this mixed profile, you have increased theta E's as moisture is transported vertically, and then it's advected across the coastal environment by mid-afternoon. On top of this as well, you've got the sea breeze adding a little bit more moisture at the surface, and then you have the additional heating from your urban heat island and your land. So you've got theta E building up in the low levels over the coast, and you've got theta E being advected, high theta E being advected across from the inland areas. So this is the combination, these two air masses, one in the low levels and one in the upper levels, which increases afternoon boundary layer instability. We've found that it's a really critical tool for predicting high-end storm days. You notice all these processes are very subtle. So they're driven by this subtropical environment where we have heating, sea breezes, and then we quite often have a bit of a trigger, such as a southeasterly change move through as well. Identifying features like this, setups which will support processes like this, working with the forecasters in the Brisbane office, we found this to be a really useful tool for distinguishing morning observations. So we get a morning sounding and it looks like a marginal environment. And working out if these processes will start occurring to be an indicator for a more severe thunderstorm environment by the mid-afternoon. Any questions before I move beyond my PhD work?
Yeah, I was curious, how you identified the hailstones using the radar, but you didn't tell us what your little technique was.
Yeah, so it was, sorry about that, I used the mesh algorithm. So we grid up our radar, we take the vertical profiles, and then we look at the reflectivity between the freezing and above. And there's an algorithm which they developed back in like the late 70s where they calibrated it, and a bit of work has been done in Shave where they calibrate that metric against hailstones on the ground. And the size is not, the correlation with the size is not perfect, but it gives you an idea whether it's going to be smaller or larger hail using that technique. It's quite simple, but it's all we had access to for this long record. Cool. If there's no more questions, these are a couple papers. If we flick the slides around later, we had one in BAM's quarterly journal and monthly weather review, looking at the experiment, the climatology, and the mesoscale from this work. Thanks to Tammy for her part in that as well. All right, so moving on to the bigger picture, the Australian radar network, and what's going on and what we have planned. So starting off with a summary of what we got. So around the country, we have a little bit over 50 radars, scattered mostly along the coast. Unlike the US, I've just driven through Utah. There's nothing in our deserts at all. So we have a couple radars. This one is almost just at a cattle station. This is our only city in this region, Alice Springs. So we have these coastal radars, and an increasing number of them are becoming Dopplerized, which is shown with the black triangle, but we still have a backbone network of non-Dopplerized radars across the country. These radars give us all-important volumetric radar data, except for still a couple up along the west coast there. So this is what we have across Australia. And there are a lot of different types of radars in our network. We have 10 different models of radars running across the country. Our big city radars are our German Meteor 150 S-bands, and our modern country radars are our digital weather service radars. They're C-band radars, so we already have different bands across the country. Below this, we have a number of C and S bands operational down to the 100 Cs, which themselves have 3 different dish sizes. And of course, CPOL in Darwin. So we have a lot of diversity in band, dish, receiver, range resolution, beam width, temporal resolution, tilts, PRF, Doppler-Nyquist, and dual pole, if we have some coming online soon. So it's a big challenge for us dealing with this diversity compared to luckier places which have more uniform networks across the country. Not only this, we have, when we're dealing with archive data, we have a lot of changes in radar technology. Just in the South East Queensland radar, just in the South East Queensland region alone, we've had 7 going on 8 different types of radars which look over Brisbane in the last 60 years, starting back with an ex-World War II service radar and up to our soon-to-be dual-pole radar in a few weeks. But using all this data, there are still ways which we can process it to compare between different severe weather events. So these 4 plots here are the 4 biggest storm events in South East Queensland. Brisbane is shown with the top blue dots in each of them. So in 85, 89, 2008 and 2014. These contours are reflectivity, so starting at 30, 40 and 50 dBz with a dashed line here. I should say that this, the 85 dataset was actually from manually traced tests, which we had to digitize for this event. But even doing that, we can still compare it to modern events from today. So it's a really powerful dataset from learning from the past.
You know, with all those different radars,
Yeah.
how the heck do you know they're calibrated at all?
It's easier.
And they're all over the place.
Oh yeah, especially the older ones. And sensitivity is so different as well with range. But with the newer ones, we have techniques now where which we can use trim. So we have 2 radars in South East Queensland.
But for the data set that you put together, your climatology,
Mm-hmm. Yeah, so
I was wondering if they were calibrated.
this is the only radar I use for the climatology.
Oh,
This one here. Yeah, so for my climatology, I just use one to make it simple. But if we want to go back before this radar, we have to start using data much older. And yeah, obviously with back in 85, calibration probably wasn't as big a thing as it is today. And as I mentioned, we're moving to dual pole in Australia, which is really exciting. So we have a program underway now where we have 4 radars in 4 capital cities being upgraded. The first one was Adelaide, down here in the south. It's been upgraded. Its upgrade is being completion. And currently Melbourne radar, Sydney and Brisbane radars are all offline for the next 4 weeks to be upgraded to dual pole. Obviously, you will be familiar with the benefits of dual pole, such as identifying different types of precipitation and improving attenuation recovery. And these benefits, there's a lot of work to be done in Australia now, delivering these benefits for forecasting, industry and research. And for my research, obviously, it's very exciting to have Mount Stapleton be dual pole enabled in the hailstorm environment of South East Queensland. So looking at our National Radar Archive. At the moment it's pretty much non-existent. It's an internal archive scattered across multiple regions. And this is a real shame because radar data sets have already been identified as a nationally significant collection as part of this Australian government policy called the Australian Research Data Services Project. So we already know it's really important. The problem now is putting it all together in one place. Not only that, the Bureau Radar Network is probably our largest remote sensing asset in Australia since we don't have an active satellite program for meteorology. On top of that, without having readily available access to data like you guys do in the US, it's very difficult for us to get radar data, and without data, there can be no science. And without science, there can be no real involvement with the international community. And finally, the current service for the Bureau delivering data, it involves a fair bit of money, a fair bit of time, and there's a lot of issues around data quality and data format. So this is all a big motivation for this project, which I'm coordinating with the Bureau and industry. And it's really motivated by the success you guys have had in the US. In particular with Nextrad, UCAR and Amazon, we have the whole archive hosted online publicly from 1991 to present. And there's been a paper recently which shows how this archive has been supporting a lot of integration with open source mapping and radar communities and innovation across industry. So it's a really important step to moving Australia forward with radar. This is the how, the real mess of it, how we've set up a framework for getting the data out of the Bureau into a location where it can be accessed freely and publicly, because the cost of access is quite high. So this is the first part of the project, is hosting the data somewhere where everyone can access it. The next part of the project, which we've been working through, is having a portal, much like Amazon. So it's a bit of a mess in Australia. We have a number of providers funded by the government which like to hand out environmental data sets. So we'll be going through most of these. And the Bureau itself, when it gets a data request, it'll be pushing clients towards one of these portals. And all importantly, data from these portals will make sure we've done a lot of work with the Python radar toolkit, Scott Collis, up in DOE in Chicago, making sure that the data service which we develop can be used very easily with the tools which are already out there for the community. We actually already run a number of radar workshops in Australia. We might only have a dozen people, but we still run them there, and we run training and workshops on how to use these data sets, and also making sure that radar is part of the long-term policy for the federal government, to make sure it's included in any infrastructure projects relating to data services. That's part of this coordination group down the bottom here. So this is the plan on how we're moving forward with getting radar data open to scientists, not only nationally but also internationally. So the archive we're building, just a few technical details. We will be running either the threads or the OpenDAP protocol, probably OpenDAP, so that you can just run a simple string of text in your command line and pull the data off. It'll all be quality controlled by an ISO standard. We have a really simple structure for getting it. We just have the radar ID, year, month, day, and the same information on the file name. We'll be using the ODIM H5 file format that's developed by EUMET. The Bureau's adopted that to move to from the older proprietary format. And also, eventually, we'll be looking at derived products as well. But at the moment, it'll just be at your reflectivity and your Doppler products. So one of the big challenges was not only getting the real-time data ready for this project, but also getting the historical data ready. So to do that, we actually ended up using Amazon Web Services. So this is a cloud-based solution where you have all your processing done in some warehouse. In this case, it was in Sydney. And we set up a number of separate servers to unpack, repair data, then perform quality control, and then push it into this cloud storage where we can eventually, if we want to do any processing, generate any stats in its own database, and then say down the line we want to push out products as well. It's a really good service for that. And why do we use clouds, a cloud service? Mainly because it scales really well. We currently have several terabytes sitting in storage and the cost is quite low. Also durability. We want something reliable if we're going to be dealing with this data set and processing it. And this is also the system I used for my PhD as well. So here's some of the outputs from the service which we're developing. We can generate really simple spreadsheets if we're looking at derived thunderstorm statistics. If you just want to get the raw data, this is a bit of Python code where in PyArt you can run a few commands and you can pull out any radar anytime you want. And of course, once you have these data sets, there's all these opportunities for visualizing it, analyzing it, and generating climatologies on a national scale. So just quickly, some users which we've got using some of these services already, which we developed at UQ, and eventually the Bureau will be taking it over. We have energy distribution, wind engineers, reinsurance, a national science program run out of the Bureau, and of course, PyArt workshops as well. Cool. Just quickly looking at climatological applications of this archive. There's a few cool things you can do with it. So I like radar because it provides a direct measurement of thunderstorm intensity, structure, and dynamics. However, it is limited by outages, range, and attenuation. Compared to previous methods of studying thunderstorm climatologies, which are primarily report-based, there's a lot of benefits in using radar data because it doesn't suffer in biases towards localities, times of days, reference objects, and the inconsistencies you have with manual reporting. While another method that's widely used is reanalysis climatologies of environments, not the actual thunderstorms. And there are a lot of fine-scale variabilities. They're not good over environments like South East Queensland, where we have mountains, coastline, agriculture within 100 kilometres. So with the radar data we have in Australia, we have in total almost 800 years now, 27 terabytes. And we have a reasonably good record. Some sites, it's a good thing they haven't been upgraded because we have an over 20-year record for some of them. So quickly looking at the applications, we've been experimenting with running generating climatologies across the country. So this is the southeast region here. This is northern New South Wales and heading up towards the Great Barrier Reef, up towards Cairns here. So we've been exploring how these radar-derived climatologies can be used as a ground truth for our reanalysis climatologies. It can be quite a powerful data set for calibrating them. Insurance companies love this kind of data, unfortunately, for their fine-scale hazard modelling and understanding the vulnerability of different communities. Energy networks, thunderstorms are a big problem for energy networks across Australia. And they like this sort of data set for looking at how much clearance they need along power lines, what their maintenance cycle should be in different areas, and looking at new corridors as well with growth. And of course, scientifically, just like from my PhD, looking at local synoptic and climate drivers, it's a really powerful data set, these long-term radar-derived climatologies. Looking at some nowcasting applications, I've actually spent the last 9 months working with industry, exploring the possibilities for using long-term data sets and improving nowcasting. This is all relating to the energy industry as well. So the biggest problem companies, particularly power distribution companies, have is predicting and assessing the impact of wind and hail damage. It's very easy to look at a radar and see a thunderstorm coming over, but it's very hard to ascertain whether you've actually had any damage to your infrastructure until someone's caught up, until you've had people drive out there and had a look. So wind gusts are the number one for energy, and they can be generated by thunderstorms, east coast lows, these are our low pressure systems, we call them in Australia, tropical cyclones, our hurricanes, and cold fronts. While large hail is also has significant impact, but fortunately it's only produced by our warm season thunderstorms, so it's a bit easier to quantify. So part of my research there was just looking at what methods can we explore for detecting hail and wind impact on the ground. So hail is an easy one. We take the science we know that we can use the mesh algorithm to estimate hail size from radar. And we have an understanding that thunderstorms with large hail generally generate damaging wind gusts as well. So if you have large hail, there's a good chance you're going to have damaging wind gusts in that area. And there's a few publications out which link particularly supercell storms, large hail, and damaging wind gusts in Australia. So we developed a technique using the mesh algorithm, which was further refined in 2009, where we vertically integrate the radar data, and we use this mesh algorithm. Let's see if I can make this a bit bigger. So we compute the mesh over the lifetime of the storm in real time, and we leave this sort of trail behind it of where we've had areas of where we expect larger hail fell. So these contours here, the storm is currently up here, but in its past, we can draw contours around the 30, 40, and 50 millimeter thresholds for mesh. You can see it quite nicely pulls out this really high impact region behind the mountains here and another higher impact region across here. And in fact, these two regions had wind gusts of over 120 kilometers per hour for this event. So if this was a really powerful tool, because straight away we can see that, well, we should be moving resources more into this region rather than here, and in particular this region as well, before they get reports in maybe an hour later that people have lost power or from crews. On top of that as well, we've been running it for a few more local case studies. All these crazy lines here are actually the energy network across a part of South East Queensland. There's a purple line running up through here, which is one of our high voltage feeders. This is our 50 millimeter contour of hail from this storm event. And this power line, one of these feeders was actually damaged right in the center of that box in this event. So it's really good for just giving an additional awareness to people who have to deal with hazards, particularly in the energy control rooms. We also had a bit of fun looking at what we can do with Doppler radar to estimate true 3D winds. So we have a lot of Doppler radars around Australia, but of course they only measure the radial component of wind. And that doesn't make a lot of sense to power companies. They don't really know what to do with that. So I had a bit of fun implementing using the implementation of a single Doppler retrieval algorithm developed by Shu 2006. And Tim Lang did a bit of work putting that together. And we ran this algorithm over our climatology and in real time to explore what's the difference between what we observe on the ground in surface stations and what we're seeing. What can the single Doppler algorithm start to retrieve? And experimenting with that approach. So the energy industry is interested in two thresholds, 70 kilometers per hour, 90 kilometers per hour. And they're contoured in the next plots. But of course, this technique is very limited in what it can do sometimes. Small wind events, particularly microbursts, no, can't see them. Radar range resolution is a big issue. When you get further away from the radar, your beam width increases. So you suffer from resolution issues quite quickly. Of course, you're not actually observing near the surface where the damage occurs. You're observing at beam height, which might be hundreds of meters above the surface. And of course, since you're not observing at the surface, you don't really know what's happening between the boundary layer, between the radar and the surface. There can be a lot of variability there. But still, it was worth exploring. Just on the right, first off, these are those contours I talked about. There's a 70 kilometre an hour contour. This is the 90 kilometre an hour contour. We have reflectivity in that colour, those colour pixels in the background. And I did a 3D rendering of this storm as well. So this storm produced widespread wind damage to the southwest of Brisbane through here. And the single Doppler algorithm picked it up reasonably well. When we look across the climatology, for the Doppler radar, which is currently 10 years long, I pulled out 104 thunderstorm events where surface weather stations recorded gusts over 70 kilometers per hour. And for these 5 weather stations, I compared them to what the single Doppler algorithm retrieved. And across the entire data set, we had an error of less. So this is the automated weather station, so our surface weather station, minus the Doppler. So this is the difference between them in kilometers per hour. And this is their probability distribution. So for 63% of cases, we had an error of less than 15 kilometers. And this is not too bad considering the radar is observing typically 300 meters above the surface weather station. And we also interestingly found a linear bias between the error as well. So there might be some potential to implement a simple boundary layer model to help improve this error from the single Doppler algorithm. All right, looking towards the future. Following the conclusion of my PhD, where we've just started a new program of science at the University of Queensland. And the theme of this program is linking the science of thunderstorm hazard detection and modelling. And we're really involving industry partners in here. They're funding a big part of the program. So we have, as industry partners, we have, of course, the Bureau, National Government and Reinsurance, Geotechnical, and Argonne as well is on there. So the purpose of this program is to implement and verify our hazard detection algorithms. So we want to not only put new algorithms and test new algorithms, we want to get on the ground and check how well they work. So the algorithms we're looking at are with our new dual pole radars. We want to look at dual pole hail, of course. We want to look at verifying our single pole hail from reflectivity only, a bit like what they've done in the US with SHAVE. We want to look at verifying our single Doppler and our dual Doppler algorithms, and look at mesocyclone detection as well, because we believe that's quite important. So to do this, we're using the Bureau's national data set as a background climatology for these algorithms, and we're also running an extensive field campaign to get the verification. The outputs from all this, we're going to develop a prototype nowcasting system, which the Bureau and industry partners can use to help explore whether these algorithms are doing any better for different cases and how they can be used in real time. And also looking at improving our climatology, which is really important. Trying to better estimate hail throughout the record in particular. This will feed into developing better hazard models for insurance. And in the longer term, we can use our reanalysis climatology and start improving it by using our verified hail algorithms. Looking at the field campaign, we'll be running this field campaign at least for 2 years, starting this October. Core instrumentation is Mount Stapleton, our Brisbane radar. It'll be upgraded to dual pole within 4 weeks and operational. So we'll be running within 150k. This is not Pecan. It's a really small domain we're working in. We have our UQ radar up and running again. So our X-pole radar, it'll be giving us, we not only have S, we'll have X-band measurements, and we'll have a second set of dual pole measurements as well. So we can start looking at different frequencies for hail detection and also looking at how well the dual pole parameters compare between the two instruments. On the ground, we have another team which will be putting out probes, so anemometers, to look at near-surface wind gusts. And we're getting some hail distrometers, hail impact sensors, which will be portable. And we can put them out with our in-situ teams as well to look at estimating hail size from hail impact. So I have a fun couple years using this gear to help verify our algorithms. And a big problem for us is we might only get 5 hailstorms a year. If we're lucky, we'll get our instrumentation in the right place for 2 of them, I reckon. So our data sets are going to be small. In Australia, we have a really thriving community of amateur meteorologists. There's Facebook groups with hundreds of thousands of people. which follow. 600,000 is the largest one, just in Brisbane. So there's a lot of weather nuts out there. And we're really reaching out through these communities, these Facebook communities in particular, by developing our own simple reporting website and Facebook page where people can quickly submit hail-size reports and upload hail-size photos of rulers as well. And we've been providing a lot of education through the local storm chaser conferences as well for this. So hopefully this will increase our number of reports as a backup for our field campaign, and I think it'll be an important part. Within the Bureau, in particular the Queensland Regional Office, we will have a forecaster on deck for briefings during the day when we run the field campaign. We're having adaptive radio sun releases, not only from our truck, but also from Brisbane Airport. We actually have forecasters working as part of their full-time employment on the program as well, collaborating on the science. And at UQ, we'll have a team of a couple postdocs, 2 or 3 PhDs, and quite a few honours projects. And this project is also spread across both engineering and meteorology disciplines. Cool. Any questions?
Okay, thank you, Joshua.
Thank you.
Questions?
Well, I'm the only one saying anything. Yeah. Well, you did bring up that you're going to do some prototyping on nowcasting capability. And I was curious if you could say a little more about that, whether it's more of just specifying what you think's happening or extrapolating things, or just say a little bit more about that.
Yeah, we're focusing not on developing anything new. We really want to take what's been done in the US and put it into practice. And we're interested first off in knowing what's happening at present. And then we'll look beyond that to see if we can extrapolate. So with like the auto nowcaster and stuff like that, that could be down the track.
Auto nowcasting, more than just extrapolating, I think it's too tight and stuff.
Yeah, but improving the inputs to Titan. So by using dual pole, so estimates of hail and that.
Any other questions? Scott.
So you might guess what I'm going to ask about, but the radar data quality is a big kind of precursor to all of those activities. Do you want to say something a little bit about the data quality activities that are going on in the radar network there? Yeah,
so our principal tool is TRIM to assess calibration. And we have a postdoc recently completed a project where we now have a module where we can easily assimilate TRIM data and compare it to our radar data. And then we have our overlaps where we can check it as well. So as part of this project, we will be checking the calibration across just for reflectivity. Dual pole is something that's very new to us in Australia. So first off, we hope the engineers do a good job when they do the upgrade. And then it'll be up to us effectively to look for any issues by using OWL, which we know is a reasonably well calibrated dual pole, and then comparing it to what they have.
You have problems with clutter?
For our mobile or for the Brisbane radar?
I guess for the Brisbane.
Yeah, so not so much for Brisbane, but lots of the other radars do. We're far enough away from the mountains in Brisbane, but Sydney radar has a lot of issues with ground clutter. So yeah, dual pole would be nice for that as well. And Alarm Pratat will be working quite a lot on ground clutter.
Quick. So you got the 4 dual pole ones in the big cities. Yep. You're going to do more? What's the plans for more?
You have to ask Alan and Aurora. So 4's pretty good because we've been waiting at least a decade to get this up and running. And they're the 4 radars which are easy to upgrade. They're our Meteor 1500S German ones. All the other ones, I don't think they're pre-fitted for dual pole. There might be a couple more, but not too many. So really, if you're going to upgrade the whole network, you'd actually have to replace the rest of the radars. So maybe a few more and 4 more in maybe 2 or 3 years, if we're lucky.
Okay, with that, thank you very much, Joshua.
Thank you.
And in case you don't know, you're going to be here another 4 weeks, I think.
Yeah, till Friday this week.
Oh, Friday this week.
Yeah.
Oh,
Short visit.
a few more days. So you get a chance to see him across Tammy, South East, Tammy Capel. Just stop by and talk to him.
Yep, I'm
Thanks,
sure I'll see
Doctor.
you all in the corridor. Thank you.